Hi, welcome back. In this lecture, I would like to describe staggered grids and go through the E scheme and describe the E lattice. So far we saw the Maxwell equation formulated as a second-order differential equation, and we come up with the so-called wave equation or curl equation. However, the Maxwell equation can also be stated as a system of coupled first-order differential equation for both E and H. In three dimensions, the Maxwell equation in a source-free region, so without J and ρ, are given by six scalar equations, 3 for the Ampere's law and 3 for the Faraday's law. So at the bottom of this slide, you can see the two Ampere's and Faraday's law. They are vectorial equations, so each one has three scalar equations. So we do not have sources, and Maxwell equation reduced to these six equations. So as you can see, these are first order equations in time and in space, and then are coupled. That means that different equations are coupled to other equations. So let's take the first one. You see here we have an evolution for the x component electric field that is coupled to the evolution of the z component of the magnetic field. The z component magnetic field evolution is determined by solving this equation. In this way, so this equation and this equation are coupled. So in the same way, here we have the variation of magnetic field in the y component, variation with respect to z, and the evolution of the y component is given by this equation here. So the first equation is coupled to this one and to this equation. So let's look at at the propagation in 1D. In this case, we can consider a plane wave propagating in the z direction through a medium such that all the quantities are constant in planes perpendicular to the x-axis. So we have x-axis, and then we have the different quantities that are constant on the plane that are perpendicular to the propagation. We assume that the electric field is oriented in the x direction and the magnetic field in the y direction. In this particular case, the 3D equation reduced to a one-dimensional equation that is the one in these slides. As you can see, we have a first-order equation, and then we have this coupling between the two equations. In this lecture, we introduce a trick. The trick used to get a good algorithm is to put the different electric field and magnetic field components at different positions on the grid. In this lecture, we talk about a space-time grid. So in the space-time grid consists of a plane where the x-axis is the space, so the grid that is discretized in space, and then the y-axis is the time. So we discretize the time in different time interval. So this is the so-called time-space grid, and we're going to discretize our electric field and magnetic field on this space-time grid. As we saw in previous lecture in this module, first-order derivatives are much more accurately evaluated on staggered grids. In particular, they have much better dispersive properties. So what we're going to do is to locate our variables in specific part of our grid. In particular, we're going to do is to locate a variable on the integer grid, and we're going to evaluate its derivative on the half grid and vice versa. So we can locate a variable on the half integer and then calculate the derivative at the integer point. And this is true for both time and space. So this is going to be true for discretization in time and space, where we are going to have this staggered grid in time and in space. So therefore, we choose to place the x component electric field on the integer point, both in space and in time. And we decided to place the magnetic field y component on the half grids, both in time and in space. Electric field is applied at integer space point indexed by r, a variable on our grid, and half integer time points indexed by n plus 1, centered and local final difference in both z and t. So let's look at this particular equation. So we have electric field component x that is defined at the integer position and integer time level, as you see, r and n plus 1 and n. Its derivative is calculated at half integer, both in space and in time. So we have, in this case, r plus 1 over 2 and r minus 1 over 2. We can apply exactly the same technique to the equation for the y component of the magnetic field and recover a very similar equation. What are the difference? Well, the difference is the y component of the magnetic field is defined at half integer point, both in space and in time. So you see here we define the position at r plus 1 half, and we take the time at n plus 1 half and n minus 1 half. So when we talk about these space-time staggered grids in 3 dimension, we talk about the E-scheme or the E-lattice. The E-scheme extends the staggering a mesh to 3 dimension with a special arrangement of all components of E and H. The electric field components are computed at integer time steps and the magnetic field at half integer time step. So this is the E-scheme in 3 dimension. It might look scary, but it is not. It's basically each of those first order one-dimensional equation. So sorry, for one components are discretized in time and in space, and following the rule that we define the electric field components at integer grid point, and then we define the magnetic field component at half integer grid points. So the E-scheme also has been used as a synonym of FDTD scheme, has been proven very successful for solving very large spectrum of problems, including microwave problems. The basic technique is that all the derivatives are centered using just one cell and are formulated as compact as possible, that are taken across just a single cell. So for the bonus exercise of our assignment, we're going to ask you to use the 3D scheme and find the eigenfrequency in a 3D cubical cavity with a perfect conductor BC. We've done that before in 1 dimension. We're going to ask you to experiment in 3D using the E-scheme. So that's the last slide, and talk to you soon.